right? And essentially, what I want to cover today is a few things. Like the artificial nose is effectively using a technique called TinyML. So today is going to be all about embedded, obviously. And yeah, over the past few months, years, there's been some really good progress in terms of making it possible to do machine learning and AI, if you want to be fancy, machine learning on tiny devices, right? And in many ways, it's really good, right? Because it means that we can make the best use of the resources, those MCUs that are sitting around out there in potentially in existing devices might still have some room for, yeah, it might be possible to make them smaller than they are today, right? And so that's what TinyML is all about. And TinyML, it can be all sorts of machine learning, right? But it starts really shining, if you will, when you start using it with sensor data, right? And using sensor data from, you name it, right? Accelerometers and so on, and using machine learning to extract some information. It's really powerful, and it's not as difficult as you may think. And that's yeah, that's also the story that I want to tell. And being an IoT person myself, I want to talk about the what happens when you combine both TinyML and IoT. So the artificial nose in question, some of you may have seen this previously on social media or wherever. It's it's the device in action, right? So it's a reasonably small form factor. The LCD display and the electronic device that you see at the back is effectively an Arduino kind of device, and we'll talk a bit more about what is in there in terms of the brain, I guess, of the nose. But yeah, it can be trained to recognize virtually any smell. And so initially, I played around with things like coffee and whiskey, but eventually I realized that it could yeah, be trained to recognize a wide variety of essential oils, maybe, or it can detect the smell of burnt food. Yeah, quite a few. I mean, it's virtually limitless, right? It really depends on how you train it. And to some extent, it depends on the accuracy of the sensors that you use. But we're going to talk a bit more about that because it might be one of your questions you already have, like what is the kind of sensor that can power such a scenario? So a few words about myself. Yeah, went pretty all in with the picture over here of the French dude with the bread and the baguette and so on. But yeah, I'm French. I live in Toulouse, and I work at Microsoft as a principal program manager in the Azure IoT team, the product team. So while most of my colleagues actually build the technology and build the cloud offering, the Microsoft cloud offering for IoT, I'm not necessarily working on the product myself, but more on being outbound in terms of yeah, advocating for the technology, creating great demos, tutorials, educational material to inspire, I guess, developers to use the stuff. And my background is with open source communities. I used to work at the Eclipse Foundation in a previous life, and so one of the things that's very dear to my heart is to make sure that we have like a great collaboration and a great story when it comes to using whatever Microsoft offerings in combination with some of the great open source technologies that are out there. And there are a lot when it comes to IoT and to machine learning, right? So, and I want to make sure actually I have the questions in the chat room at hand. So just give me a sec to make sure that my my screen is set up properly there. Yeah, whatever. Yeah, I'll keep an eye on the chat at the end. Feel free to raise any questions you may have as you have them, because yeah, I want to try and make the session as interactive as possible. So yeah, I'm French. One of the things I do, like maybe some of you, and especially during the pandemic, is that I try to bake my own bread, and I've been trying to perfect my bread recipe for the past couple decades. And while I was stuck at home early in the pandemic, one thing that I that came to my mind was, and I've had this idea for a while, was uh, sometimes like I feel like my dough, my bread, sourdough starter is looking good, and that the bread is going to be really good when it comes out of the oven, except it doesn't, right? And so baking bread is maybe not a science, right? It's hard to figure out all the factors that make a good bread and really crispy and yummy bread. And I thought that maybe whatever my brain couldn't figure in terms of identifying when is the perfect time to bake the bread and what is the perfect quality of the sourdough starter, I figured that maybe I could use technology and AI to do some of the work for me, right? And there must be, or there could be a way to literally smell and yeah, figure out whether the sourdough starter is in the perfect condition to give you and me the perfect bread, right? And so that's how I started. And I was like, okay, I kind of know that there are some gas sensors out there that can measure things, smelly things like carbon monoxide and ethyl alcohol and things like that. Maybe this could be the kind of input I give into some kind of machine learning model to train an AI to find the perfect bread recipe or the perfect bread quality. And so that's we're talking May of 2020. So like I said, it's been a while already. But back then, one of the new cool kids on the block was and still is TinyML, right? And so TinyML is the name of a technique, not necessarily the name of a product, right? Although a lot of it comes out of Google initially, but it's essentially taking things like TensorFlow, right? And those technologies for training models and running inference on machine learning models, taking the technology and making sure that it fits and it works for tiny devices. So one way to look at it is in terms of energy consumption, which is actually pretty reasonably smart to do, right? And being like, okay, we can call it TinyML if we have some kind of AI model that can run on a device with an energy cost of less than 1 milliwatt, which means that like uh, um, um, a related fact is that, I mean, if you can get to that point, then it means that you effectively make your devices smarter by means of AI and machine learning, but you still keep you still keep them very energy efficient, and you can still think about battery powered use cases, right? So the device I ended up using is it's called a Wio terminal. It's from a company by the name of Seed Studio, which I think many of you have probably come across. And the device itself is is an Arduino on steroids, essentially. So you have like the dev kit kind of form factor, but it's kind of like a dev kit on steroids because it has really nice connectors. It has like an SD card connector. It has an LCD display, tons of buttons, and I used it in combination with a gas sensor, right? And so let me just again, make sure that I have the chat here. There we go. So the yes, a bunch of connectors which I used to tap into and to get data from a gas sensor that's also from Seed Studio. That's an off-the-shelf gas sensor that actually smell things, right? It turns gas concentrations in electricity, if you will. And this particular gas sensor is, in many ways, it's not crazy accurate. It doesn't have necessarily a really good sensitivity, but it does the job really well. It's cheap, right? It's like 30 or 40 euros. So, I mean, cheap-ish. And it can smell carbon monoxide, ethyl alcohol, volatile organic compounds, as well as nitrogen dioxide. And I'm no chemist and I'm no bread specialist either, but I know that sourdough starter and fermentation in general gives things like alcohol and volatile organic compounds and carbon dioxide and carbon monoxide. So there was a good chance that this sensor would be pretty useful for my use case, right? And so a few more things, and I mean, preaching the choir here, and it might not be news for you, but I think like I will try in this presentation to share some numbers, essentially, some figures, because I think it's interesting to see how what started for me as a weekend project could eventually turn into some real product, right? And so, and what would be some of the cost considerations, some of the consideration in terms of energy consumption, scalability, and so on. So one thing that's worth noting is that what I used for my silly nose-shaped device is the Weyo Terminal Dev Kit, right? And so it's a nice one, right? It's again reasonably cheap. I didn't update the price. My guess it might have went up. It might have gone up a little bit with the silicon shortage and stuff, but it's, let's say $40, and you get a nice device. But what really matters at the end of the day, or what oftentimes what really matters when you prototype a device is that when you're happy with it, what you only care about is the MCU itself, right? And you might end up designing your own PCB. And so just like keep in mind that all you're going to hear today in terms of like the application that I built is effectively powered by an MCU, which is it's not the smallest guy you can find, right? But it's a reasonably small Cortex M4F chip. This one is a SMD51 form microchip, but any equivalent from ST and others would do the job just the same, right? I don't use any specific features or peripheral from microchip there. It has a 0.5 meg of flash and 192 kilobytes of RAM. It's like if you order it in quantities, you can probably get it for $5. I didn't check. This one might be out of stock, and maybe the lead time is a year as of today. But I think you get the idea, nevertheless. And funnily enough, like it's still plenty in terms of processing power. I could probably do with half the flash, half the RAM, which probably cut the costs in half, right? So that's something really to have in mind, I think. One thing that I realized, and I will talk a lot about what I learned, what were my assumptions when I started this project. One of my assumptions was, oh yeah, I mean, it's going to be fun. It's going to be an excuse for me to finally get my head around neural networks and machine learning and so on. But it's probably not new, right? Someone must have built an artificial nose already, like in the agro industry, in the medicine industry, cosmetics, like they must know how to do that. Turns out I was wrong. But and so that I learned, and what I also learned by extension, I guess, is that it's even worse than that. It's not only there's not that many, if at all, readily available artificial smell or artificial nose technology out there. It's actually more than that. And one point that I want to make today, you are all in different capacities embedded experts. That's not the case for the majority of the population out there, tech and non-tech people. It starts by people not necessarily knowing that sensors exist, let alone gas sensors, right? And so, and maybe some of you didn't know gas sensors existed, and then were like readily available and reasonably cheap. And the way gas sensors work, even before thinking AI, machine learning, and so on, is that you have a piece of MOS, a metal oxide semiconductor. Tiny piece of it in on the silicon, and when exposed to a current, this metal oxide semiconductor, based on what metal is actually being used, might end up reacting with some chemical compounds found in the air, right? And some electrons may end up being teared apart from the gas, or the other way around, teared apart from the MOS sensor, which long story short, causes a change in resistance in the sensor, which means that this is something that you can feed into your the analog inputs of your microcontroller, right? And so, say you have 10 parts per million of volatile organic compounds in the air, this might register as 100 ohms, and you can measure that with your fancy voltage divider and so on. And maybe you have twice or 10 times or 1,000 times more parts, particles of VOCs in the air. And this might that your resistance doubles, right? And so this you can measure, and this you can maybe start figuring out and analyzing manually, right? If then else is still a very valid construct in many cases. But what I wanted is I didn't want to bother figuring out what is the right amount of CO2, what is the right amount of ethyl alcohol in the perfect sourdough starter. I wanted an AI to learn that automatically for me, right? And so that's what I wanted to do. And a disclaimer that I want to make very, very clear here is that, at least as of 2 years ago, but it's very true in many ways, I'm no AI expert. It's even worse than that. It's to the point where for the past decade or so, I bought many books. I tried to go through many tutorials, those tutorials where they try and teach you how to recognize a really simple bitmap image with handwritten digits, right? 0, 1, 2, 3, trying to like build the supposedly the simplest neural network there is. I really couldn't get my head around it. And so this project was really an excuse for me. And it turns out that by using sensors and bread and things that are maybe more tangible than bitmaps and pixels, I finally got my head around it. And I want to try today to maybe help some of you go through the same thought process, or give you some keys as to what helped me click, help my brain click with regards to AI. So I didn't know much about AI, but what I knew was that, in a nutshell, I wanted to take my gas sensor readings and correlate those to smells, right? And to smells either in the form of it smells like coffee, it smells like whiskey, it smells like X, or findings in the form of taking gas sensor readings and getting the AI to tell me, oh yes, this is good sourdough starter, or this is bad sourdough starter, right? Whatever that means. It might not be something that smells good for a human nose, right? But it's a category of smell which I might have been interested in training my model against, right? So getting from the left-hand side of my diagram to the right-hand side, I really had no idea where to start. And so one thing that really helped me is a tool that was just getting off the ground back in 2020, but is now kind of the go-to place when it comes to all things TinyML. It's called Edge Impulse, and it's a tool suite really for not only building and training an AI model, but it's also where it really, one of the areas where it really shines is by making it really easy to acquire sensor data coming off a microcontroller, and labeling this data so that it can be used to train an AI, right? Because when you want to train a computer vision algorithm, everything happens on your laptop or in some kind of cloud environment. You have tons of JPEG images, and you just like manipulate this data that's readily available on your hard disk. When you do embedded, the data sets, they are on the MCU, right? And how do you get the data off the MCU to some kind of regular computer for the training? That's where the tool really helps. And the way it works, it's as simple as initially, what I did initially was before writing like the actual code of my artificial nose, I had a really dummy embedded application running on the device that would just read the sensor data I think at 10 hertz, right? I would like every 100 millisecond acquire the sensor readings from the gas sensor, right? And so that's one reading with CO2, NO2, VOC, etc., etc. Then another one, like all that is being streamed and output to the serial port. And then on my laptop computer, I would have a small daemon, essentially, that would just take this data and forward it to the Edge Impulse environment so that the data makes it to the cloud, essentially. And so that then I could use the Edge Impulse web-based environment to take this data and like process it and label it and be like, oh yeah, okay, this big chunk of data that just got sent to the cloud, this is sensor data corresponding to, say, whiskey, right? And so next step would be, okay, taking the data, right? And leveraging the fact that Edge Impulse makes it super easy to visualize the data. And so not being an AI expert, what I started with was my intuition, right? And so I didn't know anything about neural network architectures and whatnot, but I kind of knew the general idea, which was trying to identify some patterns, right, in the data. And so looking at the data, I was like, okay, my intuition told me that like if I acquire the data at 10 hertz, it should be reasonably, it should be fast enough. It's not like a smell and a gas concentration changes that quickly. And then I started acquiring the data, and then looking at the data, I was like, okay, yeah, it doesn't change that much, but over the course of a second or two, it may change, right? If I smell coffee or if I smell whiskey, the fluctuations of each gas might be different. Like, I don't know, let's say we're looking at the carbon monoxide here. This chart here and the data here is, I think I see it being reasonably flat, as opposed to this guy here going up pretty steadily. So I'm like, okay, maybe carbon monoxide is more volatile when it comes to whiskey. Maybe, I mean, those kind of patterns are what I thought was the kind of information it would be interesting to try and get the AI to start identifying, right? And so all these data sets, guided by Edge Impulse, I ended up processing it, right, so that it could be fed into an AI model, right? And so that's where actually I think most of the whole thing clicked in my brain. Like the raw data, really, that's what you're looking at here, right? Like if I'm to acquire 1.5 seconds of data at 10 hertz with 4 different gas sensors, those are like, I get 60 data points, right? And those are the 60 data points that we are looking at here. I'm thinking that it might be slightly less. Maybe I just trimmed the data here, but I think, I mean, you get the idea. It's raw data, right? And if I were to try and use good old programming and control structures, if these then that, right, it's pretty much impossible to take this raw data and be like, oh yeah, okay, I know what makes it characteristic of whiskey. It's going to be if the first entry is greater than the second entry. But no, I have no idea how to turn this into meaningful information. Similarly, and similar to what with the example of the pixels, right, and the single written, the handwritten digits. So the gap in my brain was, how do you turn 28 by 28 pixels, which is like really, really raw data, into something that can actually be acted upon, right? And so what I was missing is the step often referred to as feature extraction, right? Which is actually comes before AI. It doesn't. It's good old math in many ways. And so the way it works for the artificial nose is that you start taking the raw data and making sure that, one, it's shaped in a way that's sort of consistent with the reality of the data. So as opposed to just a raw byte array, I start looking at the data more in terms of, hey, it's 15 times 4 data samples, right? And then you scale the data so that you start thinking about the data, not in terms of ppm, but more in terms of no gas versus a lot of gas, right? It's more of a ratio, a percentage, if you will. So I scale the data so that it's a number between 0 and 1. It makes it easier to to approach the data as quantities that are relative to one another, I guess. And then the really interesting step, and again, something that really made my brain click, almost to the point where I was like, oh, if I get to this point, maybe I don't even need AI anymore. This point being doing digital signal processing and being like, okay, my intuition is that looking at 1.5 seconds of data is enough to figure out what the patterns might be in the data. And those patterns, one way to extract them is to do good old math and good old statistics in the form of, hey, let's look at, say, carbon monoxide. And for carbon monoxide, what is the average, the minimum, the maximum, the root mean square, the standard deviation of the gas concentration over a period of time? And this is full of information, right? Because one thing that my human brain see, and I would hope an AI model will see in just a minute, are things like, oh yeah, for carbon monoxide, it would appear that the gas concentration is indeed pretty steady, right? And it doesn't fluctuate much, or at least it doesn't fluctuate as much as volatile organic compounds. And maybe, like here I'm looking at whiskey, but if I were doing the same exercise with coffee, maybe this will be reversed, right? And maybe the the only thing I need to know to differentiate whiskey from coffee is that, for one, the CO level, whatever level it is, it fluctuates more, right? And this might be the only thing you need to look at, or maybe not, right? And so that's where you want the AI to help you figure out of all the characteristics, what are the ones that are indeed characteristic of a particular smell. And so that's the next step, which is, okay, so I have 1.5 seconds of raw sensor data. I did the heavy lifting of extracting some what I think are useful features, and then I need to step one is doing this, right? Step two is neural network, I don't know, and then profit, right? And so if I were to open a book, it would be like, oh yeah, you need to do fully connected layers and you need to have activation function and blah, blah, blah. I didn't know any of that. Now I kind of understand it better, but if I had started my work using Python and TensorFlow and some kind of like Python notebook to experiment, I wouldn't have known where to start. Luckily, thanks to Edge Impulse, they actually have some wizards that guide you and things like that. And so that's the actual architecture that I ended up building. But I often like to look at it more in terms of this kind of visualization, because that's exactly what it is. And I finally understood that an AI model is not different than a regular function at the end of the day, which you feed with whatever are the features that you're interested in. So this is the input to my function are effectively the 20 characteristics that I extracted a few slides ago, right? 4 guesses and 5 statistical characteristics, average, minimum, maximum, etc. So that's 20 characteristics in the form of numbers between 0 and 1, essentially. And then feeding that into a function whose output should be something like giving me a level of confidence between 0 and 1 of it being smell A, smell B, or smell C, for example, right? And so this is the kind of function that I want to build. And training the model consists in solving the equation so that we know what are the parameters essentially that you find here in the so-called hidden layers, so that whenever as an input there is you feed the numbers that are characteristic to whiskey, those numbers, and I like to think of them as almost as knobs, right? Like if I have a bit of this, a lot of that, even more of those two, etc., etc., then this should be routed to A, right? And it should not show up as being B and C, right? I mean, this is the kind of thing that happens when you train the model, and somehow, and I might be doing a poor job today of trying to convey this idea, but somehow it clicked in my brain back then, this idea of, okay, yeah, solving the model is just figuring out how much those knobs, how much those valves here, if you will, how often open should they be, and how much should they let such or such input go through such or such output, and how much should be routed to smell A, B, and C depending on the characteristics. So that's for the model, and that's how I trained the model. By now, I think you've realized, especially if you know more about ML than I do, that at the end of the day, this is a super trivial AI model, right? This is kind of the 101 of AI models. It's not a really complex AR architecture in any way, and yet it works, right? It actually, I achieve like 98% accuracy for whiskey, coffee, and so on. So that's actually really impressive. And we're going to talk now about what it means in terms of actually taking this and like putting this into an MCU. For that, the one of the technologies of choice is TensorFlow Lite for microcontrollers, which is in short, an optimized version of the TensorFlow framework, except that it's meant to run on small devices. So, which means that it helps with latency, right? You're not thinking about cloud and running AI on cloud resources and waiting for the result, right? And relying on network connectivity. Nope, everything happens on the device, which also helps with privacy. Everything is meant to be small, power efficient, etc., etc. And what's more, it can also leverage accelerations that you may find in the silicon, right? The likes of the ARM CMSIS or the ARM DSP functions are all things that can be leveraged for faster matrix processing and stuff like that. And it's available as an Arduino library, which makes for really easy prototyping too. So the model that you saw before, and like literally talking about the model you saw with a reasonably small architecture, I mentioned that I wanted to give some figures. How fast is it? How small is it? How efficient is it? So the model itself, to run an inference and to be like, here's my sensor data, let's run a DSP on it, extract the statistical feature, and then let's run an inference. All that requires 4Ks of RAM and about 27Ks of ROM, out of which a lot of that is TensorFlow itself, TensorFlow as a framework, and all the code, all the bytecode that you require for TensorFlow itself. The model, the parameters to the model are only 3 kilobytes, right? And then something that I find particularly interesting is that, and I should have made you guess actually, but remember the data, the sensor data, the gas sensor data, I acquire it at 10 hertz. So like every 100 millisecond, I need like a fraction of a second to use my ADCs and get the data out of the I squared C gas sensor. And once I have the data, so we are a few microseconds later, I can run the inference. And that takes 1 millisecond. And on a really, really small MCU, right? And slow-ish MCU, like a 80 megahertz. And in fact, the one I use can be overclocked to 200. So it's actually really fast, or at least it is fast when you compare it to the time, the sampling rate, right? I sample the data every 100 millisecond. Then I need 1 millisecond to run the inference, which the way I look at it is 99% of the time, right? 99 milliseconds out of 100, the device can just go back to sleep, can be idle, can do whatever else. I mean, if it goes back to sleep, that's great because it's going to be super power efficient, and or it does something else. You still have plenty of processing power for driving the LCD display and whatnot, right? And so if for some reason that's not small enough and not fast enough, there are techniques for optimizing that even further. You can look at something called quantization. You can look at something called the EON compiler in Edge Impulse, which is something that effectively looks at your AI model and compiles the whole thing into binary code, as opposed to having the abstraction layer that TensorFlow provides, which brings lots of flexibility, but it is an abstraction layer, right? So those 24 Ks of ROM that TensorFlow brings, a lot of that might be some unnecessary abstractions, which the Eon compiler can help get rid of. So that's, but all in all, I think it's really important to have those figures in mind, because that's um, and especially if, like, I'm no AI expert, right? So that I built the most basic AI model. It's small, it works really well. But if I were an expert or work in partnership with actual experts, it could be even more accurate, even smaller, even faster, right? So that's that's for the model. Something that I think is an interesting and noteworthy point in terms of, I guess, of user experience in general, and making sure that I mean, one of the caveats with TinyML is that the model being small, you might be doing trade-offs sometimes. And one such trade-off is if you have a model that's being trained to recognize coffee and whiskey, then whatever you make it smell, it will always try and tell you, hey, this is whiskey or this is coffee, right? It's not like there is a third category, which is I don't know, right? So either you train the model to have this I don't know category, or you can also rely on anomaly detection techniques to have a slightly different approach, which is more before feeding the data into your model, you can actually ask another companion model, if you will, hey, this data that I'm going to feed you, does it look anywhere like anything like the training data that you saw during the training? If not, then it's likely that it's something that you don't know. And so it can be actually really fast to do such an anomaly detection, but it's important to do it just so that you don't confuse your users and make them think that something's happening when it's not. On the topic of accuracy, actually, I think it's important to highlight that the device is really fun to use and it works really well, but it could work even better with a better model architecture. I've been talking to some flavorists and chemists, and one thing that might make sense is to, rather than just looking at 1.5 seconds of data, it would be interesting, according to them, to look at 1.5 seconds of data, but with more than one sensor, right? With one sensor that's really close to the data, to the smelly source, and one that is maybe just a few inches away, and then get those two data sets and find correlations in those in terms of, oh yeah, the smell is vanishing faster with this particular smell than with this other smell. And for that, using recurring neural networks might be useful to capture this temporality. Better gas sensors might be useful in terms of either them being more sensitive and more accurate, or them being more specific to a particular gas. Like if you care about finding out about burnt food, one characteristic of burnt food is ammonia. And so it might make sense to have an ammonia gas sensor rather than just relying on the nitrogen dioxide sensor, which might or might not pick up the N in ammonia as better gas sensors. More gas sensors might also help with so-called sensor fusion, right? Like having more gas sensors and or adding humidity, temperature, color. This might help. And this is where one thing I learned is that when it comes to AI, especially in the context of embedded and TinyML, you don't want to do too much anthropomorphism, right? And a nose, a virtual nose, you might be like, okay, yeah, it's all going to be about gas sensors, except it might not, right? If you only care about is smelling the difference between water and wine, my guess is that you're better off with a color sensor that looks at the color of the liquid. And when it's translucent, it's water. And when it's not, or when it's red, it's wine, right? That will work faster. That will not even require AI, most likely. That will be cheaper, etc., etc. Or you can do a mix, right? Which is you use the artificial nose and the gas sensors, and you add the color sensor as sort of the cherry on the cake to bring you more potential features and potential characteristics that the AI might pick up. So with the time I have left, I actually want to talk about something really important to me, which is by now, some of you might be like, okay, but this really is a pet project, and this guy doesn't even know anything about AI, and he's trying to think that to make us think that he invented the next big thing. Uh, it's just been tinkering. Yeah, I've been tinkering indeed. And again, when I started the project, I was convinced that I wasn't building anything new. That artificial noses existed already, and that using a crappy, cheap-ish Chinese low-cost sensor to do my stuff was, of course, other people must have done that. And it turns out I was wrong, right? And so I started to share about the project on social media, etc. Back in 2020, it got really popular, so it actually encouraged me to go all in, right? And I think I mentioned that I'm a pretty big open source person myself, so I ended up being like, hey, maybe I need an enclosure for the device. So I ended up teaching myself some CAD skills and some Blender skills, and I ended up designing an enclosure, a 3D enclosure for the device, which ends up being something that's effectively open hardware and something that you can print yourself. And I kept sharing about the project because I felt and I had the impression that people were genuinely intrigued. And it turns out I was right. And so there's a lesson there, I think, for all of you in tech, in terms of thinking that whatever it is you're coming up with is not necessarily crazy new and crazy innovative. Again, like I was genuinely convinced that I had my thing was stupid. And this animated GIF that you just saw, it is really stupid, right? It is the stupidest thing you can look at. It's just the device smelling coffee. It lasts 5 seconds, and yet it got people really, really excited to the point where folks on social media and influencers like this guy who has 300,000 followers, like he actually shared the video on his feed, and that's what happened in a matter of hours and days, right? Reaching out to 250,000 people, right? And this is just one single example. It ended up also being picked up by a really popular DIY magazine called Make Magazine. It ended up making the cover of the magazine. It ended up being picked up by Mashable, right? And so all in all, like it made the rounds. But one of the things I learned really, and I heard from dozens of people. So I got lucky to be viral, right? And I don't know if I have any recipes for that, except just create the stupidest GIF you can come up with. But I got lucky. But this also gave me an opportunity to get in touch with those folks that I was referring to earlier, like those chemists, those flavorists from big, like actual Fortune 500 cosmetics companies and so on, they reached out. They've been researching on the topic of smell and fragrances, etc., for decades, and they didn't know gas sensors existed. Like I'm serious, right? So that's I think that's something to keep in mind, and that's something that will stick with me, will stick with me for forever, I think, which is like, don't assume that people that the state of the art is what you think it is, right? And so not even thinking AI and machine learning, right? Like if in our industry of embedded, and some of you might be more coming from the IoT angle, like if people just start barely realizing that temperature sensors exist, but don't necessarily know about everything else that can be sensed in the physical world, then don't jump too soon to things like, oh yeah, let's do machine learning everywhere, and let's have ML ops to optimize our workflows for doing machine learning and make sure that we can roll out new machine learning models and blah blah. Yeah, we might need that sooner than later, but don't skip too many steps. Maybe is my take here. And one thing that blew my mind, and that still does, and it actually made the homepage of Hacker News. So I've been lucky many times with this particular project in being viral, and in reaching out a few additional hundreds of thousands of people. There is a kid out of California, is in 8th grade. So for those of you French people, that's quatrième, I think. So pretty young, a 13-year-old kid. As part of the science project at school, he took the device, did some research about fungal pneumonia, so a particular kind of pneumonia that's caused by fungi, right? And so in the breath, when you exhale and you have fungal pneumonia, there are supposedly some volatile organic compounds that can be measured and identified. So he was like, okay, then I guess with the artificial nose, I can train the nose to detect when someone might be sick. And that's what he did. You can look it up online. You'll find either my blog post or a video we did with Caleb, because that's his name. And that's truly mind-blowing. And that's, I mean, the way I guess this was seeded was with what I was convinced was a silly project, not worth sharing with the world, because it was just silly, using an Arduino and really basic gas sensors and hacking together a super simple machine learning model. Well, it inspired this guy to build this, and he also ended up being featured in the latest edition of Make magazine, which is awesome. And he won the California Science Fair and so on. So that's super cool. With the time I have left, and I want to also make sure we have time for questions at the end. But one thing that I did not initially when I built the project, but I eventually got to that point, especially since my day job is working in the Microsoft IoT team, is focus on this part, which is connecting the device and making it part of the IoT, right? One thing that's really great with TinyML is that you can work with fully offline scenarios, which is great, right? Because you can be even more battery efficient, and you don't have like privacy issues and so on. But there are tons of use cases where your device needs to be smart, but it also needs to be connected. Something like you have restrooms in an office building, and you want to deploy something like the artificial nose to figure out when it smells nasty and when it might make sense to send someone to clean the room, right? So one way to do it would be, you take the artificial nose, it has an LCD display on it, so that's great. Like, you just deploy it, and whenever someone wants to know whether it smells bad, they just go and look at the LCD display. But that kind of defeats the purpose, right? Because if you have to send the cleaning personnel to the room to be like, oh yeah, it needs to be cleaned, let's do it, or rather, it doesn't need to be cleaned. I didn't need to come. Then it defeats the purpose. What you want is to have the device maybe embedded somewhere in the ceiling of the room, and automatically, when it does smell bad, it automatically sends the information to the cloud, right? And so the way like it's actually reasonably straightforward to think about this particular use case. You have a device such as the artificial nose, you have the cloud, and you want the device to be capable of sending telemetry, sending signals, if you will, either the raw sensor data or things like it smells bad, it smells like coffee, it smells like whiskey, whatever. And ideally, you want also to leverage the fact that you're connected to potentially control the device from the cloud and be like potentially updating the model, the AI model, do something like initially the device is able to figure out good air from smelly air, but you do some research in your lab and there's some papers that come out, and 12 months from now, you're also able to smell COVID in the air, right? And so once you're at that point, you don't want to go in all the restrooms all around the country to deploy new version of the software. You want to do that over the air. So that's one more reason to IoT enable the device, right? And so the way I looked at doing this was by means of using the Microsoft Azure IoT Central solution, and I ended up building, going from an artificial nose, which is already something, I guess, to a connected artificial nose. And I will skip some of the slides here, but essentially taking our embedded C SDK, it was really straightforward. Really straightforward to be like, okay, out of all the data that my embedded device might produce and might manipulate, what is the data that I want to make sure to expose to the cloud? In my case, it was things like the raw sensor data, it was things like what does it smell like? And then exposing this and binding this data thanks to the SDK to some cloud properties, and then automatically the device can start reporting the data over Wi-Fi in my particular case, but could be any could be cellular, could be anything really. And once that's done, you have essentially like a full-blown architecture where you can leverage edge impulse for training the model and getting some help with bootstrapping the TensorFlow Lite based application. And then by means of connecting to Azure IT Central, you have bidirectional communications to send the inference results to the cloud and to get potentially AI model updates rolled out when you need them. But that's only the beginning, right? Like sending data to the cloud, that's not what I would call IoT, or at least that's maybe the connectivity part of it. But what really starts being really useful is when you start tinkering with the data in the form of elaborating and building some rules so that you can trigger some like actionable items based on what happens with the data. And when you start also integrating the data with your entire enterprise systems, right? So connecting the IoT device is, I believe, only the first step. What really where it really starts making a lot of sense is when you start visualizing the data, storing it so that you can come back to the data later on to do postmortems and so on, implementing rules, and maybe more importantly, integrate with your enterprise legacy systems. And that's where you start tapping into the metaverse, I guess, or the digital twins notion, which is to me much more than a buzzword. One way to look at it is taking the same use case with the restrooms and whatever is the name of this company was responsible for cleaning buildings all around, say, the city of Chicago. So they have an existing information system, right? I don't know if it's a MySQL database, whether it's something in SAP, you name it, but they already have modeled many entities, like their business entities, right? They have different buildings, and they've modeled what are the different floors of the buildings, and who are the people responsible for such and such area of the city or such and such building. There might be some integration with um, their booking system or their calendar system, so that whenever someone is out of office, they automatically manage who's going to be on duty instead, things like that. But essentially, digital twins, Microsoft has a product called Azure Digital Twins, but there's other similar solutions out there. The idea is nothing more than just adding new entities to this graph, if you will, entities that do end up having like a physical representation in the form of an actual device, right? And so this device, this artificial nose, is effectively it lives in the system, and we establish in a relationship with the particular floor of the particular building the device is being deployed in, which means that whenever the device is reporting some data, some insights, then automatically we can navigate the graph to automatically figure out who's responsible for the particular room where we detected some bad smell, and then we can automatically text them or email them or find who we should email in case this particular person is out sick today, right? So that's the notion of digital twins, right? Contextualizing the data and essentially turning, yeah, being able to leverage the fact that, to me, especially thanks to TinyML, we start getting to a point where we are building an internet of signals, right? And all those signals that need to be put in context and orchestrated, if you will. So that's what things like Azure Digital Twins may help you do, and that also helps you try and find the right balance between what should happen at the edge versus what should happen in the cloud. For example, it's very unlikely that you want the artificial nose to know who's responsible for cleaning a particular room, right? Like it's not meant to do that. Like this kind of logic, this kind of information is something that's by nature meant to live in the cloud. But the opposite to that would be you probably don't want the smell detection to happen fully in the cloud, because that would mean having to move around tons of sensor data for just like extracting a tiny signal, which you only really care about extracting uh, only on the device itself, right? So that's what I had. A few pointers. I'll try and put them in the chat too. But yeah, one, everything is open source, so you can go on my GitHub and you can get the bill of materials for the 3D printed enclosure. You can get the code, etc., etc. The schematics. You can even get all the hardware, and I don't get any royalties or anything. It's just like it's convenient for, I think, for everyone to get all the parts directly from this particular URL. There's tons of good literature that I've been working on putting together with my Microsoft colleagues from the AI team, so you can check that out as well. And yeah, with that, I think I'm at time. I didn't see any questions yet in the chat. I hope I'm looking at in the right place. But yeah, that's what I had. I will be sticking around for in the chat in the next minutes for questions if you have them by text, but also happy to take them by voice if you have time and if you are inclined to ask any. Thank you, everyone. Thanks, David and Christoph. Um, Yeah, and Christophe, you will have to tell me when I need to leave room for the next speaker. But quick question from Philip Dillon. Out of curiosity, how precise is the whiskey demo you showed in the pic? Define precise. A few thoughts here. If so, one, I'm no aerodynamics and fluid dynamics engineer. So my funny looking 3D enclosure, it looks good, but it actually doesn't work that well in terms of making sure that all the smelly molecules make it to the gas sensor properly. So putting the fully assembled nose on top of a glass of whiskey, it does work, but it might require 10 seconds or so to stabilize and to get a good reading, as opposed to just taking the gas sensor and just putting it straight on top of the glass of whiskey. That is really fast and even more accurate. But yeah, like, I mean, the accuracy can be really, really good if you have only a handful of smells, and if they are reasonably different from one another, it works really well. And even if they are reasonably similar, it does work well too, because I did some tests where I would be able to tell vodka apart from rum, apart from whiskey, apart from another kind of whiskey, which would be maybe slightly more peated. And then like all of those would, yeah, I mean, the accuracy would be 96 or 97%. So that's, I think that's good. And Youssef, yeah, if you want to unmute yourself, I don't know, I think that works, or maybe we need to move to the chat room later.